particle in a one-dimensional box. Suppose a particle is in an infinite potential well, that is the walls go to infinity, that is the potential become infinity beyond this limit. Suppose this is x equal to 0 and this is x equal to L. So this region, the potential is infinity, and for this region also the potential is infinity. And our particle is inside this infinite potential well. It is a 1D box. Okay. Inside this box, the potential of the particle is equal to 0. That is, it is a free particle. And you can see this particle motion is bounded in this boundary. Why? Because beyond this x equal to 0, the potential is infinity. So for this particle to go to that region, it should have infinite potential energy. That is, it should have infinite energy. That is not possible. Okay. So this particle is bounded in this region, that is x equal to 0 and x equal to L. And if this particle is oscillating, moving in this box, the particle become a wave and it forms a stationary waves inside this box. And my question is, what will be the wave function of the waves associated with this free particle inside this box of boundaries x equal to 0 and x equal to L? How we can find out? How we can find out? We know Schrodinger equation. What is Schrodinger equation? We know it is equal to E psi is equal to minus h square by 2m del square psi plus v psi. So by solving this equation, you see, this is an equation in terms of wave function psi. So by solving this equation, we can find out the wave function corresponds to the particle. First of all, I am going to rearrange this equation because it is more suitable in solving the problems. How we can rewrite this equation? I am taking this term to the RHS of this equation. So what we get? We get this is equal to 0 equal to minus h square by 2m del square psi plus v minus e into psi. Okay. Now I am going to multiply this equation throughout by minus 2m by h square. What we will get? We get del square psi plus 2m by h square into e minus v into psi is equal to 0. This is another form of the above Schrodinger equation. Now we can substitute the condition into this equation, that is for this free particle, potential V equal to 0. So the corresponding Schrodinger equation will be equal to del square psi plus 2m by h square e into psi equal to 0. Here this entire term is some constant value, so I am calling it as k square. So the equation become del square psi plus k square psi equal to 0, where del square is, what is it? It is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So this is a second order differential equation. Right. So I think you are already familiar with the solving second order differential equation, and there is some equation for solving the second order differential equation. Are you remembering? If you forgot those equations, don't worry, I will tell you. Okay. So we need to now a little bit about second order differential equation and its solution to solve this problem. First one is this kind of equations, that is d square plus k square into psi equal to 0, where this d square represents the second order differential. Okay. That is this dou square by dou x square and dou square by dou y square. That is represented by d square. Okay. So from this equation, we get d square equal to minus k square. So we can find out the d value, that is root of minus k square, that is I k, that is plus or minus I k, right? So this d is imaginary. If it is imaginary, then the solution will be wave function psi is equal to a e raised to ikx plus b e raised to minus ikx. So here there are two solutions. One is d equal to plus ik, that value we substituted here, and another solution is d equal to minus ik, that value we substituted here. And if you substitute for this e raised to ik and e raised to minus ikx, you get another equation in terms of sine and cos, that is a sine kx plus b cos kx. So the wave function is a sinusoidal wave function, that is as x varies. This is a sine function. You know the behavior of a sine function and you know the behavior of a cos function. It goes like a wave as x value changes. So we call these are sinusoidal functions. So the solution is a sinusoidal. Okay. And another kind of equation is d square minus k square into psi equal to 0. That is d square minus k square equal to 0. That is d square equal to k square. So what we get? D is equal to plus or minus k. Here this value is real value, right? We got two solutions, that is d equal to plus k and another solution is d equal to minus k. So the general solution will be a combination of this plus k value and minus k value. And what we will get? We get psi is equal to a e raised to kx plus b e raised to minus kx. One is corresponds to positive solution and one is corresponds to negative solution. Okay. And you see this is an exponential function. As this x value increases, the first term increases exponentially, and in the second equation if x value increases, the second term will decreases exponentially. There is no oscillation. Okay, there is only decay or exponential increases. So this is a exponential function. The solution will be an exponential function for d square minus k square kind of differential equations. Here we got the Schrodinger equation for the particle as this one. So what will be the solution? The solution will be look like this one, right? That is a sinusoidal function we will get as a solution of a particle in 1D box. That is, we got wave function psi is equal to a sin kx plus b cos kx. Is this solution is final? No, because here you see this is x equal to 0 and this is x equal to L. This is a infinite potential and particle is inside this box, and particle is restricted only in this region, that is in between x equal to 0 and x equal to L. But this wave function right now it is not restricted to this region. So right now this equation is not exactly representing the particle inside this box. So what we have to do to make this wave function exactly represent our particle? We have to modify this equation based on boundary conditions. So here what is the boundary condition? First boundary condition, when the particle is at x equal to 0, you see beyond this region there is no particle. So at x equal to 0, the wave function psi should be equal to 0. Now we have to substitute this condition in the above equation, that is psi equal to a sin kx plus b cos kx. Here see psi is equal to 0, that is equal to x is equal to 0 and this x is also equal to 0. That is a sine 0 plus b cos 0. Definitely, I think you know sine 0 is 0, but cos 0 is equal to 1. Right? So what we get? We get 0 equal to b. So we got the value of b, that is b is equal to 0. So we have to substitute this boundary condition in this equation. So what we get? We get psi is equal to a sine kx. The next term is 0. Now we have to substitute the other boundary condition. What is that? That is x equal to L, psi is equal to 0, because in this region also there is no presence of the particle. That is psi must be equal to 0 at this point. Okay. That is at x equal to L, psi is equal to 0. Now we have to substitute this condition in this equation. So what we get? We get 0 equal to a sine k x is L, right? That is sine kl is equal to 0. And when sine of some term is equal to 0, if this kl value is equal to n pi, integer multiples of pi, then sin pi, we know sin pi is equal to 0, sin 2 pi is equal to 0. Okay, so kl is equal to n pi is the condition for this sin kl to be equal to 0. So from this equation we can find out the value of this k, that is k is equal to n pi by L. So the final wave function psi is equal to a sine, what is the value of k? That is n pi by L into x. So this will be the wave function of a particle in 1D box. But again there is a problem. This wave function is not normalized. That is, we know the particle in this box, the particle may be at any location, maybe at this location or this location or this location. But the total probability of finding the particle in between x equal to 0 to x equal to L should be equal to 1. Right? So we have to normalize this wave function, then only it will satisfy this condition. So how we can normalize? I think you know the equation, that is here this particle is in between x equal to 0 and L. So the integral should be from 0 to L mod psi square dx. That should be equal to 1. So we have to substitute this equation. So the solution of this integral should be equal to 1. If it is not equal to 1, we have to make it equal to 1. That is called the normalization process. So we can substitute this psi value here, that is 0 to L. Modulus of psi square of this term is equal to a square sine square n pi x by L into dx. That is equal to a square integral 0 to L sine square n pi x by L into dx. I already told you to solve this kind of integral, that is a square into 1 by 2 into interval, that is L. So what we get? We get equal to a square L by 2. And from this normalization condition, this value should be equal to 1, right? Therefore, we get a square is equal to 2 by L, and we get a is equal to root 2 by L. Now we can substitute this a value in this equation. So we get psi is equal to root 2 by L sine n pi x by L. So this is the wave function which corresponds to a particle in 1D box. In a 1D box of boundaries at x equal to 0 and x equal to L. Okay. So this wave function exactly represents the particle inside this box. So when a particle is moving inside a potential well, what will happen? Matter waves will generate, that is, de Broglie waves will generate, and stationary waves will form inside the box. So first stationary wave will look like this one, and secondary stationary wave will look like this one. Okay, and the third one will look like this one. So different type of stationary wave can be formed inside the box. So to represent each of them, we need different wave functions, that is psi1, psi2, psi3, etc. So in general, the different wave function, that is psi n for a particle in 1D box is equal to root 2 by L sin n pi x by L. So this is a box of length 0 to L. That is why we got this L value here. So now we got different wave function associated with the different stationary waves, and definitely each of these stationary waves have different energy levels, E1, E2, E3, etc. Now we want to find out the energy of different levels. How we can find out? In classical mechanics, we know the total energy E is equal to kinetic energy plus potential energy. And here we defined the particle is a free particle, that is, inside the box the potential of the particle is equal to 0. So this term is equal to 0. That is, we get E equal to kinetic energy. And we know kinetic energy can be represented by P square by 2m. And we can rewrite this P as h cross k. Okay, so we can rewrite this expression for energy as h square k square by 2m. And just before, we found the k value for this particle in 1D box is n pi by L. So we can substitute this k value also in this equation. So we get E equal to n square pi square h square by 2m L square. That is, the energy En is equal to n square pi square h square by 2m L square. These two are very important equations. And if we consider this term as E1, energy of ground state, then we can rewrite En is equal to n square E1. Now I have a question for you. If the particle is jumping from this state to this state, so some energy will be lost by the particle and it will be radiated, okay, as photon or light. Okay, so now I want to find out what is this emitted energy when the particle is jumping from one higher state to the next lower energy state. How we can find it out? That is, this is our problem. A particle is there in some state and this particle is jumping from this state to lower state. For generally, I am considering this is nth state and this one is n plus 1th state. And we know the energy and we know the expression for energy, that is En equal to n square into E1. So this emitted photon will have an energy that will be equal to En plus 1 minus En, right? That is equal to, what is En plus 1? That is n plus 1 all square into E1 minus, what is En? N square E1. So what we get? We get this is equal to n square plus 2n plus 1 into E1 minus n square E1. That is equal to 2n plus 1 into E1. That will be the delta E. That is the emitted energy. Now let us consider a particle in a 1D box and it is in a ground state. What is the wave function of a particle? Psi n is equal to root 2 by L sine n pi x by L. It is a wave function of a particle in a box of length L, right? So for the ground state, the n value will be equal to 1. So the wave function is psi 1, that is equal to root 2 by L sine pi x by L. Now my question is, what is the probability? That is, here this wave function is normalized. That means if you are integrating the modulus of this wave function over the region 0 to L, you get a value equal to 1. But now I want to find out what is the probability of finding the particle from 0 to L by 2 and what is the probability of finding the particle in between 0 to L by 4. So we have to know the equation for probability. What is the probability to find out a particle in a region A to B? It is equal to integral A to B modulus of psi square dx. What is this modulus psi square? That is nothing but psi star psi. Okay. So to find out the probability of finding the particle from 0 to L by 2, what do you have to do? We have to find out integral 0 to L by 2 modulus square of this wave function, that is 2 by L sine square pi x by L into dx. What is its solution? Okay, this is equal to 1 by 2. I think we already solved this problem, right? And if you are solving this probability of finding the particle from 0 to L by 4, that is integral 0 to L by 4 2 by L sine square pi x by L into dx, what we will get? Actually, this problem also we already solved and we got the solution as 1 by 4 minus 1 by 2 pi. And the probability of finding the particle in the region L by 4 to L by 2 is integral L by 4 to L by 2 2 by L sine square pi x by L dx. This one is also we solved earlier and we got the answer as 1 by 4 plus 1 by 2 pi. That is, this is the 1D box. And for the ground state, the wave function will be this one. Okay, this is the first stationary state. And if you are partitioning this into L by 2, that is, this is 0, this is L, and this region is L by 2, and we are partitioning here, that is L by 4, and this is 3L by 4. Then the probability of finding the particle in this region will be equal to 1 by 4 minus 1 by 2 pi. And probability of finding this particle in this region will be equal to 1 by 4 plus 1 by 2 pi. And you know, for this region, the probability will be same, and for this region, the probability will be same as this one, that is 1 by 4 minus 1 by 2 pi. So what will be the probability of finding the particle in this region? That is adding these two terms. So what we get? We get 1 by 4 plus 1 by 4, that is 1 by 2. Here also adding these two terms, what we get? 1 by 2. So this is the probability of finding the particle in the various region of 1D box of length L. Okay. Now expectation values. What is the general expression for finding the expectation value? Suppose we have an operator O and we have to find its expectation value, then expectation value of O operator is equal to bra psi operator get psi by bra psi get psi, right? That is in integral form, integral psi star operator psi dx or d tau. Maybe it have a spherical symmetry, then we have to use this d tau. And if it is a 1D problem, then we have to use dx or dy or dz. Okay, by integral psi star psi d tau. Okay, so this is a general expression for finding the expectation value. So here I want to find out the expectation value of x operator. So what we get? This is equal to integral 0 to L, because 0 to L is the region where the particle is present, into psi star x psi dx divided by integral psi star psi dx. Here this one is a already normalized wave function, so this value definitely will give you equal to 1. So we have to bother only about the numerator. So what is this value? It is expectation value of x is equal to integral 0 to L psi star, that is root 2 by L sin pi x by L into operator, that is x into root of 2 by L sin pi x by L into dx. What we get? This is equal to, we can take this outside the integral, that is 2 by L integral 0 to L x into sin square pi x by L dx. So here what you have to do? You have to convert this sin square pi x by L into another form. Then only you can do this integration, that is 1 by 2 into 1 minus cos 2 pi x by L. You have to substitute this equation in this integral and do the integration. I told you some trick to solve this kind of integral. So use the trick and finally you will get the answer as L by 2. That is expectation value of x is obtained as L by 2. Second one, expectation value of x square, that is equal to integral 0 to L psi star x square psi dx, that is equal to 2 by L integral 0 to L x square sin square pi x by L dx. This integral also we already solved and we got the answer as L square by 3 minus L square by 2 n square pi square. This one also we solved earlier. Okay, are you remembering? Okay, next one, third one, what is the expectation value of px? That is expectation value of momentum. How we can find it out? We can find out the solution of expectation value of p by substituting its operator, that is minus I h cut tau by tau x. Okay, so this operator will act on this wave function and finally it will give a value. So it is a little difficult problem, it's a lengthier problem. I think you are remembering we took a much time to solve this integral, right? So similarly, solving this problem also, it will take more time. So is there any way to solve it little easier way? Yes, there is a way. What is that way? We know the idea of momentum, that is P is mv, and here specifically it is px, that is it is equal to mvx. What is this v? Velocity, that is m into dx by dt, that is px is equal to m into dx by dt. What they are asked to find out? The expectation value of momentum. So we have to take expectation value of this entire term. So what is the expectation value of m? M is a constant. Then what is its average value? M itself, that is expectation value of px will be equal to m into expectation value of d by dt of x, that is nothing but d by dt of expectation value of x, where this expectation value of x we already found. What is that? That is equal to L by 2. So just substitute this value here. Then what we get? L by 2 is a constant value. So the time derivative of this constant value is 0. Therefore, expectation value of px operator is equal to 0. Why this average value of momentum is 0? because we know the particle is moving in the forward direction and also it is moving in the negative direction. So this momentum will be positive momentum and this will be negative momentum. So when adding or taking the average of momentum, it will become equal to 0. And when we are finding out the average value of position, that is 0 and L, the average value we will get as L by 2. Okay. Now fourth problem, the expectation value of px square. Again, you can solve this problem by substituting, we know px value is equal to minus I h cross dou by dou x. So when you are taking px square, you have to take the square of this value and you have to take the second derivative of the given wave function, and finally you will get the answer. But it takes time. Is there any simple way? Yes. What is that simple way? We know the energy is equal to kinetic energy plus potential energy. Here we are dealing with a free particle, that is the potential energy of the particle is 0, that is E equal to kinetic energy, and kinetic energy can be written as p square by 2m. So we can rewrite this expression, that is p square is equal to 2m into E. Here what is the question? You have to find out the expectation value of p square, that is expectation value of 2me, that is expectation value of p square is equal to expectation value, that is average value of 2m. 2m is a constant value, so average value is same as that one, into expectation value of E. What is this expectation value of E? That is the energy value. What is the energy value of this wave function? That is En is equal to n square pi square h square by 2m L square. So this 2m will cancels and we get expectation value of p square is equal to n square pi square h square by L square. So we got the solution in just 2, 3, 4 steps. Okay.